Okay, so let's start with this problem for today. Practice 72, page 72, number 1B. Okay, this one actually is easier than the one from yesterday. Why? The one from yesterday was two good or two bad vectors. The one from yesterday, the last one we did before the day was done. They were both bad vectors. Both of them needed to be what? Decomposed or broken down. What kind of vectors do we have here? Well, we have a mass of 1.2 times 10 to the 2, or just 120. Everyone go ahead, just write 120. 120 kilograms. There we go. 120 kilograms. Okay, with a force of 1.5 times 10 to the 2, so 150 newtons. Which direction? North, only pure north. What kind of a direction is north? Good or bad? North is good because it actually falls perfectly on the vertical axis. And another force it's subject to of 220. Which direction? West. West is another what? Good direction as well. The question is just like yesterday. Calculate the acceleration of this object. Calculate the acceleration of this object. What Newton's law has acceleration in it? First or second? Second. The only one that has acceleration in it is second. So technically, at the end of it, at the end of this problem, we have to say A. You don't write this down. Just this is the last step of the problem. We have to get A equals F net divided by what? Divided by mass. So the first thing we have to get is what? Is the net force. Okay. How many forces do we have? How many? Come on. Two forces. One of them is pointing, and one of them is pointing. Perfect. So that means north and west would just be what? Up and left, and there's absolutely no vector decomposition. So the first thing we're going to do is sketch. So I'm going to erase this. Hey, Rod. Um, okay. So uh, there we go. Yes. So go ahead. Since north could be done here and west, we'll do it here. Oh, which one is longer? Which one has a longer magnitude? West. So just make sure you scale it nicely to make sure that your angle also makes sense. So maybe like this. Yeah, I'm going to erase some of this one. Yeah, that's good. All right. And now we're ready. Okay. This one is north, and this one is west. And this one is 150. And this one is 220. How do you add these two vectors? What do you do now? You're already at the what? At the xy done completely, so you just do Pythagorean. So go ahead. Uh, from yesterday's notes. Oh, good. Yep. So we just do the dashed line to can finish the parallelogram, or in this case, a perfect rectangle, just in this case. And then you connect. Boom, done. Bless you. Okay, obviously, which angle do we always go for? Horizontal, which means it's always got to be this one. I want this angle, and I want this magnitude. Okay, I believe you have a slide for this calculation. No, you don't? Okay, so let's do the calculation really quick next to this one. So F net equals square root of what? Of the 150 squared plus 220 squared equals, I don't know, um, 150 squared plus 220 squared equals, and then you square root the whole thing. There we go. What's the sig fig situation here? 3. So is it 2? Okay. So 266, is it closer to 260 or 270? 270 for sure. So 270 Newton. Okay. Now let's do the angle, theta. So theta equals, and let me just minimize, shrink this one a little bit. Go ahead. You can just keep going with the calculation. Right. All right. Perfect. Theta equals tan inverse. You always divide what by what if you want the horizontal angle? Which component by which component? Y, x. Perfect. So you got to divide the 150 by the 220. So 150 by 220 equals, I don't know how many, but I know it's less than 45 degrees for sure. So 120 Sorry, I mean 150. 150 divided by 220 trig second and 10 inverse. This up to 2 sig figs, that is 34 degrees. 34 degrees. Apparently, they went with what? 56 degrees. Doesn't matter. 56 plus 34 is 90, which means we're both good. Okay, so that means immediately I can actually jump to the A step. So A equals, and now we're going to divide. So we're going to divide what? The magnitude, which is 270 newtons, divided by the mass, which is 120 kilos. What am I missing still from here? The what? The degrees or the direction. So if my direction is going to be horizontal angle, it's always going to be horizontal first, vertical second. So it's going to be west, north. So west, that's you. West, north, 34 degrees. I'm going to zoom in so you can see. There we go. Okay. West, 34 degrees north. What is 270 divided by 120? It definitely is 2 point something because 120 could fit into 270 twice. So apparently, yep, 270 divided out by 220, 120, 2.25. 2.25. What is 2.25 up to 2 sig figs? 2.3. 2.3. In what unit? It's acceleration. So standard must be what? By the way, technically, if you put newtons over kilograms, are you still correct? What do you think? From the equation itself, newtons over kilograms, is it also the same unit for acceleration? Well, according to the equation, yes, it is. I'm seeing some puzzled looks because they're like, how come? You said that acceleration is always measured in what? Meters per second squared. But everyone, pencils down. Now you have to understand that you can always, once you learn something new, you can always think of it in a different way. So in a kinematic perspective, from a kinematics perspective, acceleration is always measured in what? Meters per second squared. But when you involve forces and masses, it could also be represented as what? Come on. Newtons per what? Per kilogram. That's it. How do you prove it? You go back to the units. Look. Can someone remind me again what's a single Newton? What's a single Newton? Remember the one trick? Come on, what's the definition of a Newton? It's like you're saying F net equals ma, but instead of using the equation, you're using the unit. Come on. One Newton. Sorry, 1 Newton equals what? One what? Kilogram mass accelerated by how much? 1 meter per second squared. Okay. I have here what? Newtons is being divided by what? Okay, let's do that. By the way, this is a very common thing in physics. It's called unit analysis or dimension analysis. Physicists and engineers always do it as the first step to even knowing if their equation makes sense or not. Okay, so divide by kilogram, technically 1. And here you divide also by what? Kilogram. What happens here? Which ones cancel? From the right side. The 1 kilogram. This one cancels this one. So what do we conclude? 1 Newton over 1 kilogram is always the same as what? 1 what? So a Newton per kilogram is also the same as what? Meters per second. Is it making sense now? Again, it's the same, only if you look at it from what? From a force mass perspective. Okay? And guess what? Could we probably define acceleration another way when we do work on energy and momentum? Probably we will, because we're going to use another set of units to still relate it to that equation. Okay? So it's fine. However, acceleration is always like conceptually better thought of as meters per second squared or newtons per kilogram. Yeah, because you always want to relate things to motion. Always want to relate things to motion. So it is what it is. Sorry, meters per second squared. In which direction? Same thing. West, 34 degrees. North. Check. Done. That's it. That was an easy one. Why? Because both directions were good directions. No need for a breakdown. Okay. All right. Let's go to the second problem. Finally, an actual what? Newton law problem. Okay. By the way, this kind of problem is super, super common in first year. Okay. Let's read the problem together. Okay. So we have, okay, I told you that friction is how many kinds? Two kinds. This kind is called what? Static friction. What is static friction? It's the friction on a system that's moving or not moving. It's basically the friction that holds everything in what? In place. Like, for example, if I'm trying to move Kinder right now, don't worry, just gotta pull on the chair. I'm actually putting in some force, yet she's not moving. If this was on ice, would she be moving? Yeah, because ice is what? Is a very smooth surface. It doesn't take much force to what? To make something move on ice. But she's not moving, which means what? There's definitely a force canceling me. That's called what? Friction, and it's related to static friction. Okay. Once I start you moving, I'm still going against friction. But what kind of friction would that be then? Kinetic, because I'm in motion. It's not trying to stop me. It's trying first to slow me down, and then it tries to stop me. Okay. So the static friction on. So we have this system. Okay. This is called a system because it's made of what? Of multiple objects. Okay. How many objects do we have in this system? If you can count. You can say three: a block, another block, and a wall. Okay. And by the way, technically, could you count this knot or this like little dot as an object? Yeah. I mean, technically, they all have to combine in one point. Okay. So the static friction on one block. Which block do you think here is only the one subject to friction? B or A? Which one is actually being stopped by friction directly? A. B is not under friction. Can you tell me actually what forces are under A? Which you need to know because you're going to have to sketch an FBD for everything here. What? Gravity pulling it down, but it's not moving, which means what? Something is yanking it up, which is tension. Is it under any other forces? No, no more applied forces, no more normal, and no friction. How about this one? Okay, everyone. What's the first force on A? Definitely. Gravity. What's counteracting gravity? Okay, done the vertical ones. Now, is this rope pulling on it? Of course it is. It's trying to what? To slide it this way. If this was on ice, would it slide? Of course it would, but it's not, which means what's not pushing, but what's stopping it this way? Friction. Exactly. There's friction between the bottom of the block and the what? And the surface of the table. You got it. Okay. So what do we have here? We have the block A has a what? Has a weight. Usually I don't give you weight. I give you what? I give you mass, and I expect you to calculate the what? The weight, or FG, force of gravity. Okay? Well, this one already gave you the what? Already gave you the weight. By the way, if I give you the weight, can you calculate the mass on Earth? What's the equation that relates mass and weight? What's the equation that relates mass and weight? Okay, here's an easier way to say it. What's the equation that relates mass and force of gravity? See, when you say that, we're like, oh, Fg equals mg, right? So if you know the force of gravity, and you know the m, and you know the g, you can know everything, right? Well, which one do you know here? When you know the weight, which one do you know? The Fg. And on Earth, definitely, g is always what? So instead of multiplying, what do you do now? You divide. So if you always divide the weight, the physical weight, not the English language weight, because usually when someone asks you how much do you weigh, you don't give them what? Next time you sign up for a gym membership, screw with them. Weight, write 623. Right? Technically, you're right. You're correct because they ask you for your weight. Right? Don't write newtons though, because you might actually have someone who actually knows physics. Right? Write 623. They will think that you're talking about what? Kilos or pounds, which makes no sense. But you actually talk about what? You're talking about newtons, which means you divide it by 9.8, and then you get your own mass. Is it making sense? So if you always want to know the mass from weight, just divide that number by 9.8. If you're on what planet? How about if you're on the moon? Does anyone remember what was it for the moon? When you calculate 1.6, 1/6 of Earth. If you divide the Earth by 6, you get 1.6. Okay. So block A is being pulled down by how much force? 6.5. Sits. Again, what does sits mean? Sits means not what? Not in motion. Good. And it's connected to a wall by a string. Yes. Block B, that hanging one, has a weight of how much? So right off the bat, it has a lesser mass than A. Is attached to a string. Sorry, and it's connected to block A. everything is connected to point B. The string from block A to point B is what? Is perfectly what? Yeah, we could have lowered the table a little bit to make it angled. By the way, we're going to do a problem like that, but let's start things slow, okay? The magnitude of the force of what? Of the force of what? Friction, stopping the whole system, is how much? 1.4 newtons. Okay. So let's look at the first slide, everyone. Let's go to the first slide. Okay. Draw an FBD. Remember, FBD means what? Stands for what? Free body. Which means I have to tell you which body to look at. Which body is part A concerned with? Block B. Where is block B? Right there. Okay. Tell me again what were the forces on it? Come on. Tension. Always start with the most fundamental one. Because remember, tension, gravity are like a cause and effect, right? The cause is gravity. The effect is what? Like one of them it starts first and the other one reacts to it. So go ahead, write FG. FG. But it's FG on what block? B. So let's write it FGB because technically we're going to also have FG on A, just to distinguish which forces belong to which one. Okay. Tension is here. You can put it inside of the rope or next to it. Oops, sorry. Okay. What's the symbol for tension forces, usually? The easy way? Capital T, yes. T. And technically, are we going to have another tension here? So let's distinguish them by subscript. Is this tension coming out of block A or block B? Great. You could have called them T1 and T2. So TB. Any motion direction here? Any direction of motion here? No, there isn't. Great. So are we done the FBD? Would you get full marks for this FBD? Yes, you would. You showed me the forces, at least the symbols of them. You don't need to worry about numbers now. You showed me that there is no direction of motion. If there were, you would have to put it on. And that's it. Okay, great. Is this moving? What Newton law? First, what is Newton's first law? It's a very simple equation. What is it? F net equals 0. Great. So now you can go to the slide after, I think. You have, oh, sorry, to the space next to it. You have a space next to this. Okay, so what do we write? We write no motion. No motion means F net equals 0. Am I missing something on top of the F net? The arrow. But did I already give you a direction? Sorry, did I already give you a diagram? Did we show you direction? Great. Let's start with what? With scalars. Just like we did with kinematics. Same way. Okay. Bless you. So 0 equals, sorry, 0 equals. But okay, everyone, I'm going to show you an extra step that I don't need you to do from now on, but I'm just going to do it for today. Question. Technically, do we have directions here? Yes, we do. So we always have to choose what? We always have to choose a positive direction. But when things cancel out and make 0, does it really matter which one becomes positive and which one becomes negative? No. How? Then I go with what? I like to go with math. Up is positive, bottom is negative. So everyone, just add a double-headed arrow here, and put positive here, and put negative here. Okay. Now you tell me which force is pointing positively according to the designation we just made. Tension. Great. So positive TB, positive TB, and which force is pointing negatively? Gravity minus FGB. How can you arrange this equation? You only have one thing to do. What do? You move the what? You move one of them to the what? To the other side. Which one is smarter to move to the other side to make things positive and nice? You move the negative FGB to the TB. So that means you get FGB equals what? TB. Could you have started with that equation? Question, everyone. When two things cancel each other, whether they're numbers or vectors, what do you know about those two things? They must be what to each other? They must be equal. I am okay with you 100% if you jump from this step to that step. You know what's going to happen. Okay? Sorry. So which one of those do we know the value of? Do we know the value of FGB or of TB? Yeah, they're asking me for the magnitude of tension. What was the weight of the hanging block? 2, done. That's it. By the way, statics problems are harder than this. It's more than just doing this and finding the number and equating it to it. But as a start, this is usually how they start. 2.8 equals to TB, which means tension in part B of the string or in the B string is 2.8 Newton. 2.8. Do you need to tell me that tension is 2.8 newtons pointing upwards? If you want to put it as a force statement, sure. Sorry, as a vector statement. But come on, you know my style now. You already gave me a diagram. You're good. Done. That's it. Same thing, but this time we're diverting our attention to which block? Draw an FBD for block A. Okay, how many forces were on block A when we discussed it? 4. 1, 2, 3, 4. 2 on each axis, and each 2 pair is opposite to each other. All right, so let's start. FGA. FGA. What reacts to it? Say again. Do you need to call it FNA or just FN is fine? Why do you is there such a thing as FN on B? So that means what? Since we have only one normal force, why give it a subscript? It's the only one that exists. So FN. All right. Okay. What is pulling that way? A string, which means tension. I'm sorry, say again. Okay. Well, you're right. It is technically applied what on the okay. So it's a force applied by the what? By the string on the block to pull it. But since it exists in a string, what do I call it? I call it tension. Okay, everyone. Any force existing on a string in a string, rope, cable, chain, what, even your skin, anything that could be deformed or stretched or compressed is called tension. So tension, but in what? In A. And what's stopping it? Friction. I like to put friction here, where it really happens. There we go. Friction. What was the symbol for friction force again? F, F, F. There you go. Oh, great. Not next week. So yeah, actually next week. Next week, when we start actually incorporating what? FS and FK, we're gonna call it what? FS. You're right. But for today, I actually chose problems that have friction, but without telling you what kind of friction it is. Okay. So next week, we're gonna actually branch out and deal with each friction on its own. Good observation. All right. Any motion here? No. If one part of the system is not moving, most likely the rest of the system is not either. Okay. But we have to choose what? A positive direction for the x-axis, a positive direction for the y-axis. Since nothing is moving, what do you go with? You go with math. So which ways are positive? Right and up. All right. So maybe we could, I don't know, above them, you can just put a grid like this. There we go. Positive, positive. All right. How many axes do we have for this problem? We have 2 axes. We have the horizontal one and we have the vertical one. Is there any motion on either axis? What can you tell then about each pair of forces? They must be what to each other? Perfectly opposite to each other and equal to each other. Exactly. So what's the question? Determine the magnitude of the tension in the horizontal row and the magnitude of the normal force acting on block A. So they need what? They need both this guy and this guy. Do you know how much the weight of FGA is? Yes, you do. So you can start analyzing this one first. Do you know how much force of friction is stopping the whole thing? You also do. How much? 1.4. So you can start by analyzing this one. Doesn't matter. What's up? What did you say? Seems too easy because it's meant to be. Again, I told you, any statics problem is actually more complicated than this, even with the number of inputs you have. This is just the beginning one. I'm just using this one to show you how many things could happen, and still everything is what? 0. And you're going to see that we're still going to do some angle work in part C. But you're right, it is easy because it's the easiest statics problem you can actually see. Yes. Okay, I have a question for you. If the tension, okay, hold on this. Okay, is it moving? No, pull. Is it moving? right there, you know that my force and your force have to be what? Okay, pull more. If your force is bigger than this one, things have to start what? Moving in an accelerating way. But they said it's not. So that means what? Everything has to be what? Sorry, say again. The friction. By the way, could friction ever push things its way? No. Exactly. So that means what? If friction is equal to that, nothing should move, right? If friction is bigger than that, also what? If friction is less, something should move. Since nothing is moving, at least we know, at least, that those two have to be equal. Thank you, at least. That's the whole idea. By the way, could this surface be super rough? Could you make a super rough surface? Yeah. If you make it a super rough surface, to move it, what do you have to keep doing to tension? Keep pulling, or keep increasing the force on it. So at least I know that whatever tension is here is equal to whatever the friction needs to give to keep the system in check. Do you see what I mean? You're right. Next week, to Ali's point, next week, when I start giving you what's known as, how many people remember coefficient of friction from grade 11? Yes, it's something that relates the roughness of the surface to the roughness of the other surface. Then you can know how much of tension you can actually need to pull just to start it moving. Make sense? It's like when you're trying to push, nothing is happening. And that's how much you need to clear it by. Okay? So that's next week. All right. So let's start with the, well, the first one they want is the tension. So let's start with what? With horizontal. Okay. So x-axis, no motion, which means what? F net on the x is equal to what? Is equal to? Great. Immediately you can jump to what statement? What is equal to what? Only on the x-axis. TA must equal what? FF. Done. That's it. So TA equals FF, which means TA is equal to, what did the question give us for the force of friction holding block A in place? 1.4 Newton. Done. That's all we have to do. No force analysis, nothing. More like a balance analysis. Okay. Let's do the exact same thing for the what? For the y-axis. Y-axis. I don't have, oh, sorry. I don't have space, so I'm just going to go below. Y-axis. No motion. Which also means what? F net on the y equals 0. So what is equal to what? Fn must be perfectly balancing FGA. Fn must be perfectly balancing FGA, which means Fn has to be equal to, what was the weight of the block, the table block? 6.5. Done. That means you have to make a surface that's able to withstand a what? A normal force, or able to give a normal force of 6.5 newtons. Okay. Nora, what's part C? So we've done an FBD of the hanging block. We've done FBD of the table block. Okay. Everyone, imagine if you didn't have just a knot. Imagine if you had a small ring, like a, imagine that you basically had a ring, and the ring was what? Subject to how many tensions? 3. Who said 2? It's actually how many? 3. A tension pulling it down through the gravity of this, a tension pulling it this way through the tension of this, and a tension pulling it up here. Okay? How many forces do I have on the ring then? 3. All of them are what forces? Tension. By the way, are you given the, okay, technically, does this not, or does this ring have mass? Can anything not have mass? Only one thing doesn't have mass, photon, the particle of light. Everything else must have a mass. Which means technically, if they give you the what? If they give you the mass of the ring, what other force must you also sketch on it? Force of what? If something has a mass, it also has what? Gravity on it. Did they give you the mass? So if you don't know mass, you assume what? By the way, get used to this. In physics, a lot of things are called massless, or negligible mass. What does that mean? The mass of the ring is very what? Small compared to all the other what? All the other masses in the problem, compared to this guy, compared to this guy, and so on. Do you see what I mean? Just to simplify the math. And by the way, don't think that this is only a grade 12 principle. Even in first year physics, you will always hear, oh, negligible mass, negligible friction. Obviously, the more complex the problem gets, you have to consider mass and friction and so on to be real to the analysis. But oftentimes you're like, you know what? It's so small. Even if we incorporate, it's just going to mess up the math so much. And it's really not going to change the final answer by that much. Yes. Uh-huh. Yes, we do not account for the what? For the gravity force on that ring. It's completely what perfectly canceled out by just the three tensions, and that's it. Again, as a theoretical thing, okay? And this happens a lot more than you think. All right, so how are we gonna sketch the FBD of this? First of all, is this a 2D problem or a 1D problem? 2D. Look, we have tension along the x and the y, and even tilted. Well, the fact that you have it along the x and the y makes it 2D anyway. So what do? I always like to imagine I have a what? I have a portable grid with me, and I can use it at any moment I please. Where should I put this? Where should I put the bull's eye of this, like the crosshair? Exactly at the object I'm interested in being the FBD. Boom. All right. So right here. Is it making sense now? Imagine you always have a crosshairs with you, and you just put it wherever you like on the diagram. So how many bad forces do I have? Bad forces. Just what? Just one. Which tension? The tension along what we can call tension A, tension B, tension C. How many good tensions do I have? Great, perfect. All right. So what am I going to do now? Nothing. I'm just going to basically impose what? Impose the XY on it. All right, go ahead. So just honestly, just make, sorry, just make, just basically just make a axis this way and extend this one. Go ahead. Rulers, anyone? What's up? Okay. How many forces are acting on this one? Three forces. One tension is pulling this way, one tension is pulling it this way, and one tension is what? Pulling it this way, right? So my question now is, remember the net force problem we did 2 days ago? Person A is pulling this way, person B is this worksheet. Okay, how did you actually sketch them? You sketched three things coming out of the center, right? Perfect. Three things coming out of the center, and then you what? Whatever needs to be decomposed gets decomposed. Whatever doesn't need to be decomposed stays the same. I want you to actually imagine three actual people. One, you hanging this way, like actually hanging from a rope, someone pulling this way, and someone pulling this way. Yet this is not moving, which means all the forces somehow have to do what to each other? Add up, subtract out, or cancel out. Cancel out. That's exactly what I'm trying to do now. I'm going to try to do the math for them what? Canceling out. Okay? All right. So everyone, let's put a y here and an x here. And obviously, let's put a plus here and also a plus here. Okay, let's put the vectors on it. Okay, I guess this one would be pulled down, so tension. So this is TB, TA. And we said we're going to call this one what? Yeah, I mean, we have AB, might as well call it. You can call it just T because it's a distinctive one. DC. Yes, go ahead. Uh-huh. I need to break down. Yes, exactly. Everyone, there's a center ring there, and three people are pulling on it. TC is pulling that way, TA is pulling that way, and TB is pulling that way, yet everything is doing what to each other? As a whole system, everything is nullifying or canceling out each other. Okay, which vector needs to be broken down? The only one. TC, TA, and TB are perfectly on the grid axis, so they don't need to be broken down. So, so you have, okay, all right, so you did. So everyone, just show a little bit of a breakdown here and here, if you can. Can we do TA and TB and then basically just, flip it like we did with the other problem the other day, you can definitely do that for sure. But this is actually a good chance to show you. And remember, okay, how many people remember the first way we did it the other day when we canceled the force, when you used cosine theta and sine theta? Raise your hand. Was it easy or long and elaborate? Okay, but good. Okay, I could do your way, which is the other way I did, which was what? Add the other two and what? And what? Flip. But I'm going to do it in a different way. I'm going to do it Josh's way. Josh suggested a method which is way less elaborate than what? Than the way we did before. Okay? Check this out. Everyone, pencils down. Don't worry about cosine or sine for now. Just worry about which axis does each force fall on. This force right here. This force right here. Is this TC on the y or TC on the x? This is TC on the y. How about this one? TC on the x. So instead of calling it TC cosine theta and TC sine theta, I'm just going to call them what? TCY and TC what? That's exactly what you did the other day, which I totally agree with. So let's do it that way. Trust me, it's going to lead to a much, much, much quicker calculation than the one we did. So go ahead, TCY. And this would be TCX. Okay. TCY must balance what? TCY must balance what? No. TCY must only balance TB. And TCX must only balance what? Great. So we can just say what? X-axis. You know what? We're not going to say no motion. We already know it's not. So we're just going to say what? Oops, sorry. We're going to say TC. TC what? TCX equals TA. So that implies that TCX is equal to how much? How much was TA? We already have. Okay, good. Again, I could make mistakes. No problem. TCX equal to what? It was 1.4 newtons. Thank you. Okay, again, y-axis. TCY is balancing what? TB. That implies that TCB is equal to, I think it was 2.8 or 6.5? 2.8? Okay, all right. What was the 6? Oh, 6.5 was the weight of this guy. Yes, sorry. Okay, what do I do now? I've got the X, I've got the Y. The same steps every single time. What do you always do once you get the X component and the Y component figured out? Pythagorean and 10. All right, so that means TC is equal to the square root of 1.4 squared plus 2.8 squared. Okay, who's got this? I want to stay on this screen. Come on. 1.4 squared plus 2.8 squared. Come on, people. Phones or calculators. Go. Sure, yeah. Nice. How much? 3.1. Bingo. 3.1. Perfect. So 3.1 newtons. What's next? Angle, theta. Theta equals tan inverse. Now, I know we always divide what? What by what? Y by x. That is correct, which also is what we need to do here, right? What if the question wanted me to find the angle on this side? Exactly. So technically, if I don't give you an angle, I just ask you to find the angle, you always choose the horizontal, please. If it shows it to you, you just have to be careful which one it's demanding you to find. Well, good news, it's the same one we always find, which, by the way, is like a habit. So what's the y? Oh, sorry, I forgot here. Did I say TCB? Whoa, my mistake, everyone. This should be what? TCY. My bad, everyone. TCX, TCY. So go ahead and erase, unless you had it right the first time. Good for you. TCY. Sorry. TCY. Yes. So TCY, which is 2.8, divided by 1.4. That's a perfect 2. So the only angle that has a tangent of 2 is 63, which is 2 sig figs is 63 degrees. Check. Check. You see Josh's method? Much easier and much less what? Labeling with cosines and sines. And Josh, which one did we end up finding first? The angle or the magnitude? The magnitude, and we also found the what? The angle. Mine, we found the what first? The angle. And then how did you find the magnitude? You had to what? Sub in, which technically means if your angle was incorrect, your magnitude would also be what? Incorrect as well, because you're feeding in incorrect information. So obviously, this is the way we're going to do it from now on for what? Because it's easy. Yes, someone had their hand up. Thank you. Good. All right. That's it. Obviously, since you have all of this done and you have a diagram, you do not need to tell me right 63 up. You already are telling me which way. Done. Okay. So you see that it was an easy problem, right? But it evolved into this still. Yes, because it has an angle in it. All right. Perfect. Good. Okay, let me see if we can do. Ah, yes. Let's do this problem. Those ones are so common in first year. Elevator problems. Okay. All right. Everyone, pencils down. Let's just read it first and see what's going on. All right. So, two blocks are fastened. What does fastened mean? Connected or tied into how many? A string or two strings? Two. By the way, could you connect both these to the same string? I don't think you can. If that if this whole thing is one string, that means this string is what? Going through the block, which means what? Can the block actually hold itself, or would it just slide through the string? So that means what? Technically, this is an independent piece of string than what? Than this one. Okay? All right. So two strings inside of an elevator. The mass of the top block is how much? 1.2. Mass of the bottom block? 1.8. The elevator, with all its contents, is going which way? But not just any up. It's going up, and it's what? Boom! Right there. This problem is purely what law problem? The entire problem, the whole thing is what? Second law, because everything here is moving what? Is moving up in which way? In a what? In a constant motion way or an accelerating way? Once you hear the word acceleration or deceleration, you immediately jump to what law? Second law. Do you see what I mean? Remember the second step? You have to decide if it's first or second. This is not telling you, but it's telling you the what? The key word that basically tells you exactly what equation to use. Okay. What's the question? Ragad, sorry, Janan, what's the first question? A. Calculate the what? The tension in what? In each string. I have a question for you, everyone. Which part of the string do you think is under more tension? How many people say the top one? Okay, Ali, why? Why would the top one be under more, or be like tensed more or stretched more than the bottom one? Okay, so I'm talking about why is this rope under more tension than the one below it? Yes, thank you. Eventually, it's responsible for what? For pulling up how many masses? Really two. But how many masses is that one, the bottom one, actually just pulling up? Just one. So that means this one effectively is pulling up how much? But this one is pulling up how much? 1.2 plus. You got it. Exactly. That makes perfect sense. And then, what's the maximum tension in the strings? Sorry, maximum tension in the strings can be what? 38. How quickly could the elevator go up in an acceleration way such that the strings don't what? I mean, okay. Question. Do we have the rope, the little thread? Anyone see the thread, the little thread? So it was here. Nope. What? Sorry. Ah, there we go. Don't worry, I'm not gonna hang sorry, blocks to it. No, I'm just gonna do one thing. Am I pulling on it? Is it breaking? What now? What happened? So that means what? But when you pull quickly, you do a faster what? Exactly. So that means what? Okay, question. What if I have this string, everyone, and I hang something from it, like I hang my keys, okay? Let's say my keys are heavy. And I just pull up slowly. Would this string break? Probably not. What if I pulled quickly? Yes. Why? Because when you have a higher acceleration, you have a what? Higher net force. Exactly. But does it make sense? That's as easy as an explanation. Just basically what? Every single time you yank something, you subject it to more what? To more acceleration, which basically is what is more force, right? So that means if this elevator would suddenly go up like this, what could happen to the rope? It could snap. And that's the question. If they could take as much as 38 of force, how much could you allow the what? The elevator to go up, but without them what? Snapping. Make sense now? Always remember the snapping principle. Okay. So let's actually what? Start. So, okay, how many objects do you have in this problem? Okay, technically you could go crazy, right? You could say 2 blocks, 2 strings, an elevator, the cable. What are the real interesting objects in this problem? The what? Are the strings interesting, or are they just connection mechanisms? So what things are actually what being moved by the strings? The 2 blocks. Thank you. So how many FBDs are we going to sketch? Can you tell me how many forces are on the bottom block? What forces are acting on the block 1.8? Definitely number one is what? Gravity. And what? A couple of tensions or just one? By the way, just so you know, everyone, when you sketch an FBD, okay, everyone, technically, is this one still pulling on this one? Directly or indirectly? You never sketch indirect forces. Only the things connected to the object. So this one is under how many forces only? Gravity and which tension? Only this part. How many forces is the top block under? Okay, who would like to say them? Ali. Okay, T1. Which one is T1? Okay, so this one is subject to the tension, pulling it up. Keep going. The tension obviously pulling it down. And then it's on what? Its own weight because it's still in the Earth gravitational field. Is there any normal forces on the blocks? Nothing is supporting in this way. So that means that's it. Perfect. Okay, let's start with the FBDs. All right. So you do have that slide. Awesome. Okay, perfect. So let's sketch. Let's everyone go ahead and pull this part out of the what? Out of the elevator. So we're gonna sketch this one now. All of them. So we're okay. I know that we're not supposed to sketch what? Multiple FBDs together, but let's do that. And then on the second slide, we'll split them up. So, oops. Oh, like this. So I'm just gonna sketch this block, and then this box. Yeah. Oh, I know, and that's why I said you wouldn't. Okay. In university, you would have to do what? One split. Sorry, two split. And that's what I'm gonna do in the second slide. But I like to what? Pull the part of the system that's relevant first, and then what? And then split it into two. Is it making sense? Again, I'm taking a lot of liberties with FBDs, but this just was my style. I guarantee you, don't do it my way in grade 12 and first year, you will lose marks. Okay? But I'm just trying to what? Just trying to ease you into the process. Okay? I don't want to split it from the beginning. I want to split it after we understand why it's being split. All right. So I guess there's a chunk here or a string part here and a string part here. Okay. So this is 1.8 kg, 1.2 kg. All right. So what force is here? By the way, you can sketch the force coming out of the object, sideways, sorry, to the side. It doesn't matter. Okay. What force is this? Gravity. So, oh, okay. Let's call this, everyone, let's call this mass 1 and this mass 2. So this would be FG2. Okay. Oh, sorry. No, no, no. Okay. Let's not sketch it coming out of it. Let's sketch it actually near the string itself. Like this. Yes. Okay. How many strings do we have? So I can't call both of them T. I need a T1 and a T2. Let's call this T2 because it's only connected to M2. Sorry, not connected. It's connected to M2. I know it's connected also to M1, but we just have to choose something. Okay. How many forces on the top one? We said 3. Okay. FG1. Right? Now, how is this tension, everyone? How is the tension here acting on this one? Is it pulling it up or pulling it down? Yes. You read my mind. You basically oversaw the evolution of this problem. Yes, it will, but just hold on until we do the problem. Yeah. And then what's pulling up? T1. The whole system is moving where? Upward. But is it moving up in a uniform motion or accelerating motion? Yeah, you have to decide because if you do uniform, you have to do F net equals 0. If you do accelerating, you have to do F net equals ma. So just go ahead and say ACC. No need to write accelerating. ACC motion. All right. Now we're going to split the two diagrams. I actually want you to do a line right here. Just give me a second. I'm going to choose a different color. Let's go with blue. I'm going to split it right here. Do you see how we have now two distinct FBDs? Raise your hand if you see it. Yeah, we have an FBD here purely with 2 forces, and we have an FBD here purely with 3 forces. Okay, so let's go now to the next slide. Perfect, we have it. So we just have to put the impressions, the labels on the diagram. Oh, sorry. Okay, everyone. So this one was subject to T1, but also what here? Tension, T2, and FG, did we call it 1 or 2? We called it 1. All right. Oops, sorry. And this one, what was pulling up? Tension what? No, 2. Remember, tension 1, tension 2, tension 2. Yep. And then what? FG2. You got it. Okay. Positive, positive. Okay. Now let me see how much space we have. Okay, we're good. Okay, everyone. I want you to split the screen or this slide into 3 parts. Just hold on. We're not done yet. This part here, everyone, we're going to do the equation for this. This part here, we're going to do equation for this. And this part here, we're going to combine the equation. You're going to see what I mean by that. So, but relax. Let's do this one. F net equals 0, F net equals ma. Come on that one. On all of them, F net equals what? Since it's accelerating motion, ma. Okay, so let's start. F net. So this points to this one. Okay. Oh, okay, everyone, which force is positive? Which force of 3 forces here? Which one is only positive? Come on, focus. Okay, go ahead. Positive. Sorry, positive. Positive T1. Okay, which forces are negative? Yes, so positive T1 minus T2 minus FG1. Go ahead, go ahead. What's Fg to any object on the surface of the Earth? Who said? Okay. Everyone, is the force of gravity just 9.8? That's only G. What's the force of gravity? It's m time. By the way, one of the biggest mistakes, even in first year, you just ask, what's the force of gravity on this table? And people are like, oh, 9.8. Hold on. If you're saying it's 9.8, that means you're telling me that the force of gravity on this table is 9.8 Newton, which means it has a mass of how many kilograms? 1 kilogram. They missed the part where they multiply by the m. What if I ask what's the gravity of acceleration? So what's the acceleration of gravity on anything at the surface of the Earth? That's what. That's 9.8, and you stop right there. Is it making sense? So force of gravity needs both gravity and what? And your what? Your mass. Thank you. All right. So T2, T1, sorry, T1 minus T2 minus M1G equals M1A. Can someone tell me how many unknowns we have in this equation? How many things you don't know? Okay, what are they? What variables are you do you not know the values of in this equation? We don't know T1, we don't know T2, and we also don't know what? We also don't know. Actually, we do know the acceleration. Everyone, look at the problem. Do we know the acceleration? Yes, we do. How much? So, how many unknowns in this equation? Can you solve a single equation in two unknowns? No, you can't. So, what do you do with this? You box it because you know you're going to get back to it. All right, everyone, go ahead and box this equation. What do you think my next step is? Come on. I am done. All I can do with that mass. What should I get my attention to now? The other mass. Perfect. So now we're going to do this analysis. F net also equals what? MA, still MA. Okay. What are the forces on this object? And FG. Which one is pointing positively? Great. Come on. You're seeing the trend here. What's my next step? I only can do one thing. Say again? Exactly. Rewrite the FG as a product of M times G. How many unknowns? How many? What is it? Yes, apparently this one could be solved right now for what? For T2, because I know M2, I know G, and I know what? And I know A. Awesome. So go ahead, put a check mark here, check mark here, check mark here, check mark here. Okay, so let's do that. T2 minus. What's the mass of, come on, 5 minutes, we're done. What's M2? 1.8 times, actually, let's just put brackets. It's got to look nicer. 9, come on, no, 9.8 minus, or sorry, equals 1.8 times what? Times, you said 1.2? Okay. How are you going to solve this equation? Uh, 2, sorry. Yeah, so we're going to have to multiply these two, move it, so it becomes plus. So equals, T2 equals, and some 1.8, 11. What's 1.8 times 11? 18 and 1.8. Is it 19.8? Yes. How are we going to find out T1? Yes, you box equations that you know you're going to revisit. So that means T1 minus 19.8 minus 1.2 now times 9.8 equals 1.2 times 1.2. Who's got this? I don't. You have to get this guy, move this one, and move this one. Come on, let's hear two answers. I know we have only 2 minutes. Come on. By the way, I only know one thing. It has to be bigger than the T2 equals 19.8. Because we said the top rope is under more tension. Because it's effectively holding up the entire system. 2 blocks. Who's got this? I just want the answer. When you move everything, effectively you're going to add up the 3 turns. Come on. NASA supercomputers, come on. How much? How many people got exactly 33? It is 33. And the logical check is that it's bigger than the bottom rope part. 33. Done. That's it. That's it.